Hi, good day all of you. Welcome to our session. Welcome to our channel, Intelligible Tutorials. In this today's session, already we have discussed regarding the orthogonal boundaries in our previous videos. Okay, what are the systematic boundaries? What are the incomplete boundaries, and how they can be represented? And how the systematic boundaries can be represented, and how orthogonal boundaries can be represented. In the previous video, we stopped at the orthogonal boundaries, right? So we completed the systematic boundaries, we completed the incomplete boundaries. What are the properties? What are the things to be there in the incomplete boundaries? How to overcome them? All these things, some of the things relevant to the incomplete boundaries, like unachievable path and variable not exist, all these things we have seen. Okay, and we have already seen systematic boundaries. So how these incompleteness can be converted in a way by adding some set of the constants like c and k. Okay, so these are the systematic boundaries. Next, we are going to discuss about the orthogonal boundaries. In our previous video, we stopped regarding the orthogonal boundaries, right? Okay, so two boundary sets u and v are said to be orthogonal if every inequality and one minute, every inequality and v is perpendicular to inequality of the v. Like that, see, this is the inequality of the u, this is the inequality of the v, completely perpendicular with one and each other. Because these inequalities can be tested independently, we can't test them combinedly, right? Okay, so that's what it is saying. Whenever the inequalities will be there in two different kinds of the boundary sets, if two boundary sets are orthogonal, that means perpendicular to each other, having some set of the inequalities, and they can be tested independently. You have to test the u boundary separately and v boundary separately here. It's like this, u and v are perpendicular. This is called as u and this is called as v. You have to test it separately and you have to test this one as the separate one, right? So like that it can be represented. Such kind of the boundaries are called as orthogonal boundaries. Now what are the tilted boundaries? Tilted boundaries are, these are the examples of some tilted boundaries. These are having some kind of the tilts here, all are in unique direction, all are following single direction. These are called the tilted boundaries. Okay, so next one, linear non-orthogonal domain boundaries. Okay, so these are the linear boundaries. First of all, they are completely linear and not completely perpendicular to each other. Not perpendicular to each other. Okay, so that's why these are called as non-orthogonal boundaries and as well as the linear boundaries. Okay, so here it is the linear, the line equation. Here you are directly representing what is the linear equation. Y is equal to mx plus c. Here also y is equal to k1 plus bx, where k1 is the constant. Okay, okay, and y is equal to mx plus c, the line of the, it a straight line equation, that is. Okay, so it is in the form of y is equal to mx plus c. Okay, so where c is the constant. Next, here coming to the line number 2, it is also in the form of the linear equation. It is also in the form of the linear equation, and we are having some set of the x values. X is equal to a1, a2, a3, a4, a5. X values already given. These are the k values are constants, and these are not perpendicular to each other, just crossing with each other. So that's why these are called as non-orthogonal and linear boundaries. These non-orthogonal and linear boundaries can be represented like this. Okay. Next, closer consistency. The closer consistency is one of the property of the nice boundaries. Okay, so nice boundaries are consistent. Closer consistency, having complete boundaries. All these things are the properties. Previous video I discussed regarding the properties of the nice and ugly domains. Okay, so boundary closures are consistent and systematic. In the previous thing, the shaded areas are there here. The some of the shaded areas are there, are on the boundary, denote that boundary belongs to the domain in which the shading lies in the boundary lines belong to the domains on the right. Okay, so consistent closure means that there is a simple pattern to the closure. For example, using the same relational operator for all boundaries of a set of the parallel boundaries. Okay, so the shaded areas of the boundary denotes that the boundary belongs to the domain And consistent means they use the same relational operator. What it is now we are going to see here. For example, here the lines are, the shaded area is there. Okay, so what is this area, shaded area represents? The shaded areas on the boundary denote that boundary belongs to the particular domain. The shading lies on the boundary. See here, the shaded lines are there. These shaded lines, whatever points are there, those are belongs to this particular domain only, but not the other domain. That's what it is saying. Okay, so whatever the points that are lying on this boundary, that are lying on the shaded line, these are also belongs to this particular domain only, but not other, none of the other domains. It belongs to this particular domain only, right? And next one, what is the meaning of the consistent closure means? Consistent closure means whatever the equations are there, the linear equations, here they have to satisfy the same relational operator. Here y is equal to is used in the linear equation 2 also. The same is used in the linear equation 3 also. It should not be used as greater than here, or somewhere it is lesser than and somewhere it is greater than or equal to, like that. They are following the same linear relation, same relational operator here. Is equal to, is equal to, is equal to. Okay, that feature is called as what? Consistent closure. Whenever we are following the linear equation, the same relational pattern, the same relational example, then so the same relational operator for all the boundaries which are parallel to each other, then we can say that is called as the closure consistency. Closure consistency means it should have to follow the two different kinds of the properties. The first property is being parallel boundaries. Next one is nothing but using the same relational operator. Whenever those are parallel, obviously they may use the same relational operator. Like y is equal to mx plus c, here also the same equal to, here also the same equal to, and here also the same equal to. So like this we can represent the closure consistency. Closure consistency is one of the property of the nice domains where they can maintain the parallel boundaries and they can have the same relational operator for all the boundaries, right? Okay. Next, we are going to another property of the nice domain, that is called as being convex. What is the meaning of the convex? The geometric figure on any number of the figures is convex if you can take any two number of the points on the two different boundaries, join them by a line, and all the points lie within the same figure. Okay, so being convexity is one of the, whenever you join two lines, okay, they form a straight line. Okay, and do you join two different boundaries, join them by a line, and all the points on the line within the figure, whatever see whatever points you can see, whatever two different boundaries you can join them, all the points lie on that particular line only. Okay, so this is one point, this is one point, so both the points lying on the same line, that is the meaning of the convexity. Okay, so this is one example of the convexity. This is one of the property of the nice domains. See, nice domains are convex, whereas dirty domains are not convex. Dirty domains will look like this: some line here, some line here, some line here. So whenever you can join this, it form like this, or it form like in a zigzag manner, but not in the straight line. Okay, so this is the example of the ugly domains. Okay, these are the example of ugly domains. These are the examples of the nice domains being convexity. Okay. Next, simply connected. Nice domains are simply connected. There is no complexity at all. They won't exhibit any kind of the complexity. Those are completely simply connected. Okay. So one there are any one piece rather than pieces all over the place interspersed with other domains. That means completely connected with each other. One is connected with each other and another one is connected with each other. There is no complexity will be represented. Simple convexity is a weaker requirement of the convexity. So it is also one of the property of the convexity by simply connected. So all these are interrelated properties with the nice domains, so simply connected and convexity and all these things. Okay, if a domain is convex, obviously it is simply connected. Okay, so consider the domain boundaries defined by a compound predicate of Boolean form ABC, and input space is divided into two domains, one domain by ABC and therefore the other domain is defined by its negation. So what are the domain boundaries that are defined by the Boolean form ABC is completely connected, and it is simply connected. Okay, now these are the properties of the nice domains, and now we are going to see the ugly domains and what are the important properties of the ugly domains. Already in the previous video I discussed regarding the properties of the ugly domains also. Once again we see what are the properties of the ugly domains. Let us see the properties of the ugly domains once again. Non-linearity, incomplete, non-systematic, inconsistent, non-convexity, complexly connected, having holes in between. These are the various properties of the nice and as well as the ugly domains. Okay. So now see what are the other things added to the ugly domains. Okay. So ugly domains. Okay. Some domains born ugly and they are having the ugly bad specifications, incompleteness, inconsistency. All these are the bad specifications. Okay, so every simplification of ugly domains by programmers can be either good or bad. Okay, they can search for nice solutions and simplify essential complexity out of existence. Whenever there is no complexity, they can simplify, then they can become it as the nice domains. Tester in such brilliant insights will be blind to essential complexity and therefore miss important cases. Whenever there is the complexity is there, some of the important cases will be missed. Okay, if the ugliness results from the bad specifications and the programmer simplification is harmless, then the programmer has made ugly good. Whenever it's not complex and he made it as the simplification, then it becomes the nice. Okay, so ugly good means nice. Okay, so we have to remove the by this what we can conclude is we have to make the complete to incomplete to complete, inconsistency to consistency, and bad specifications to good specifications in order to make the ugly domains to the nice domains, right? Next, it is also having some other properties like ambiguities and contradictions. What are the ambiguities? Domain ambiguities are there. What are the domain ambiguities? Normally, some holes are there in the input space. Those are called as the domain ambiguities. The holes may lie within the domains or in cracks between the domains. Two kinds of these contradictions are possible normally. Okay, these are the ambiguities. And what are the contradictions? Normally, one domain is overlapped with another domain, one closure is overlapped with another closure, then these contradictions may happen. So ambiguities and contradictions are also best properties of the ugly domains. Okay, so pictorially we can see how they can be represented. Okay, now see here in this example we are having the domains. This is A is one domain and B is one domain. Capital A is one domain, see here. Okay, and capital B is one kind of the domain. Both are overlapping with each other, and ambiguities are there. Ambiguities are nothing but incomplete values. The holes are there. These are ambiguities. And contradiction, that means some line will be there. The contradiction is existing. Dual closure will be existing in between the domain. This is called the example of the contradiction, and this is the overlapping, and this is the missing boundary is there. There is no boundary at all for the B. This is missing boundary. So all these are some irregular, incomplete, inconsistent things are showing here in the domains A and B. These are also some of the added properties of the ugly domains. See here, the holes are called the ambiguities and overlap domains, and then boundary is missing here and contradiction is showing here. Like this, these are so many misspecifications or bad specifications are existing in between the domains A and B. Right. Okay. So how can we simplify that particular topology? How can we remove these things? Now we are going to see. Okay. The programmers and tester reaction to this kind of the complex domains or ugly domains is same, simplifying them simply. Okay. So there are normally three generic cases: concavities, holes, disconnected pieces. Okay. So programmers introduce bugs and tester misdesign test cases by normally these concavities or holes can be removed by smoothing out concavities, filling the holes, and joining disconnected pieces. The best example of the concavity is nothing but missing boundary. Okay, missing boundary is one example of the concavities. So how can the testers can do this? by filling those holes, by smoothing those boundaries or concavities, or by joining the disconnected pieces, right? Okay, so see how they can do pictorially. We can see here. See, they can making it the convex like this, and they can fill the holes, and they can join disconnected pieces like this. Okay, it's irregular. They make it as the regular, making the concave convex, and the next one filling up the holes like this and joining two different things like this. Disjoint things can be joined like this. Okay, so these are the right things they can done by simplifying the topology. Okay. If domain boundaries are parallel but have closures that to go everywhere, the natural reaction is to make closures go the same way. Okay. So the domain boundaries are parallel. We can make them as the closures. Okay. So that means we can remove any inconsistencies or any irregularities are there. We can remove them and we can make it as a regular, complete, and as well as the consistence. Right. The next one is forcing closer consistency. What is the meaning of the forcing closer consistency? That means some tilted boundaries will be there. Those should be maintain some unique direction. Just now I told in the previous video, previous slide like this. See here, where we have seen this. First example I will show once again. We have already seen this. See the here, all are maintaining the unique lines. All are maintaining the unique direction, the same direction. Okay, from the up to bottom to top they are showing. Okay, not in non-unique direction. Okay, so now here we are seeing the same here. See, here it is different. This direction is different and this direction is different. Here's just see, and this direction is again different. So we are making in the consistent direction like this. All are making in the unique direction from left to right. Okay, so here also the same, forcing the closer consistency. We are making it as a closer means we have to make it in the form of unique direction. Here also there is no unique direction. We have to make these tilts in the one boundary itself like this. Okay, there comes in one boundary only. So this is right and this is wrong. Right? Okay. So these are the various properties of the nice domains and as well as the ugly domains. And these are the other added things, ambiguities and contradictions of the ugly domains. And we can simplify such a kind of the topologies like removing the concavities, filling the holes and joining the disconnected pieces like this. And as well as by satisfying the making the unique direction and making completely consistent like this. Okay, so like this we can make the simplifying, we can make the complex topology into the simplifying topology, and we can make the ugly domains into the nice domains. In the coming video we talk about domain testing strategies, what are the various kinds of the domain testing strategies and domain bugs, all these things. Okay, so if anybody won't subscribe my channel, please subscribe my channel. Thank you for watching. Thank you.